Okay. So you should hear your computer Zoom program saying that this meeting is being recorded. Do you hear this?
Yes.
Okay, good. So now that means that it works. Very good. Vector fields. So this is the question, and well, you can try to construct a non-vanishing vector field, but most likely you will fail. So a first kind of result in differential topology asserts that there are no non-vanishing vector fields, and in fact, you can even count the number of zeros of a vector field. Well, one has to give a meaning to this because, first of all, a vector field may have infinitely many zeros, and even if it has finitely many zeros, you have to compute the number of zeros with multiplicities. Well, this can be, well, one can give a meaning to this, and the Gauss-Bonnet theorem in this very special case asserts that the number of zeros counted with multiplicities is equal to 2. Okay, so if you're familiar with this, then most likely you know
Could you please
a
repeat
good half of the course. Well,
could you please repeat the statement?
The statement is that the number of zeros of a vector field counted with multiplicities, which I haven't yet explained, is 2. Okay? So, well, again, a good half of the course will be devoted to really to give a meaning to this and proven, of course, not only for a sphere, but for a smooth manifold. We'll see that the number of zeros is related to the Euler characteristic of the manifold. Okay. So, well, now I want to start the course proper. So let me start by defining the main object we are going to talk about. So let's start by well, let's say that our topological space space M is an n-dimensional topological manifold if it has 3 properties. Well, one is that I assume that M is Hausdorff. Secondly, I want to assume that M is has a countable basis. And lastly, and this is really the most important property, is that every point on my space has a neighborhood, exists open neighborhood P containing P and a homeomorphism. Homeomorphism from U to an open subset in Rn. This is open. Okay, and I will call it phi. So, locally, a topological manifold is a topological space which locally looks like an open subset in Rn, and of course I can arrange my U so that U is actually homeomorphic to an open disk in Rn or even the entire space, Rn itself. So it's locally homeomorphic to Rn. This definition is somehow it's implicitly assumed here that this number n, which is called the dimension of n, is well defined. So, and this is a non-trivial fact theorem that n-dimensional manifold is not homeomorphic to m-dimensional.
May I ask a question?
Yeah, sure.
The point 2, M has a countable basis. Why do we need countable basis? Just
why do we need countable basis?
Yes, why are manifolds defined this way? Why is it suitable?
Well, perhaps the reason, well, we haven't yet proved any results on this, right? So definitely it's not needed for dimension for this statement. For me, the main, we will use it, the existence of countable basis when we will talk about partition of unity on manifolds, even integration. But kind of personally, I don't know any reasonable examples when property 2 fails. So this is, we will see how we're going to use 2 later, but this is really, this is not a restrictive condition at all. The most important condition is 3. So, okay. So what is the statement here? So the statement is, the statement of the theorem is that an open subset of Rn, yeah, unless, of course, unless, let me finish this, unless n is m. So really the statement of the theorem, the assertion is that an open subset of Rn cannot be homeomorphic to an open subset of Rn unless n is equal to m. That's the assertion. So in particular, it means that Rn is not homeomorphic to Rm for n is not equal to m. So in fact, this corollary is really the key to the theory. It can be quite easily derived from this. I'm not going to prove this in this generality. We will see later a proof of the fact that Rn, there is no a smooth, well, a diffeomorphism between Rn and Rm, if n is not equal to m. So the proof of this stronger assertion that these spaces are not homeomorphic, it actually belongs to algebraic topology. So, for example, how can you check that R is not homomorphic to R2? Well, so let's see. Example. So R is not homomorphic to R2. Well, what is the proof? How to see this?
Of point.
Yes, remove a point. So if you have a homomorphism, then it would induce a homomorphism. You just pick a point, P, look at its image. So you take, for example, R minus 0, and it would be homomorphic to R2 minus phi of 0. And you know that this is connected. And this is not. So the idea is that from the point of view of algebraic topology, some topological homological invariants of R minus Rn minus the origin and Rm minus origin are different. For example, you can, if you know what the singular homology is, the most understandable proof uses singular homology. And you show that for these spaces, for Rn minus the origin and Rm minus origin, singular homology are different. So therefore, these spaces are not even homotopy equivalent. Okay. So, but this is that's again not.
No, these spaces clearly are homotopy equivalent because they are both.
No, when I remove the origin, when yeah. So the first idea, of course, that from homotopical point of view, Rn is homotopy equivalent to point. So the first idea is to remove one point. Consider Rn minus the origin and Rm minus a point. And these new spaces, if a homomorphism between Rn and Rm would provide a homomorphism between the complement, between the punctured spaces. And in fact, these punctured spaces are not even homotopy equivalent. Very good. So now so this is that's for topological manifold. So now I want to define a notion of a smooth structure on a topological manifold. So let's first go back to this definition. This definition. So it asserts that a topological manifold can be covered by open sets, and such that each open set is homomorphic to, say, Rn or open subset of Rn. So let's say that a chart on M is a pair consisting of consisting of an open subset of M and a homeomorphism between U and an open subset phi of U in Rn. This is open. Okay, this is phi. So now an atlas on M is a collection of charts arbitrary collection, UI, VI. It can be infinite. And I do not even assume that it's countable. With such that this UI cover the entire space. So by definition of a manifold, any topological manifold has a chart, has an atlas, sorry. So now imagine that we have an atlas. So I have I can cover my manifold with open sets, and for each open set, we are given a homeomorphism between this open set and the open subset of Rn. So let's draw a picture. So this is my manifold covering by charts, and and I have some maps to Rn. So this is Vi, and maybe this have here Vj. Okay. So then, so if I look at, so this is Ui, and this is Uj. So for each pair of open charts, we can look at the intersection, and on the intersection, we have actually two homeomorphisms. We can look at Ui intersected with Uj. So this map Phi takes this intersection here to some open subset, maybe something here, and also I can use Vj to identify this intersection with an open subset here. So that means that if I look at Phi of this is this open subset, I can use the composition, which is Vj composed with Phi inverse. So I first identify this open piece with this intersection, and then I apply Vj, and this lands in Vj of Ui intersected Uj. This is a homeomorphism, and everything lives in Rn. This is in Rn, this is in Rn. So this is a homeomorphism between two open subsets in Rn. Okay? And this is called the transition maps. So whenever I have an atlas, whenever I have to fix an atlas on a topological manifold, for every pair of indices, I have these transition maps between homeomorphisms between open subsets in array. Now I'm ready to define a smooth structure. Well, let's say that so an atlas let me give a name to this. So it's a collection of open subsets and homeomorphism between UI and open subsets of array is said to be smooth if all transition maps are smooth. For every I and j, these compositions phi j are composed with phi I inverse are smooth. Okay, so actually, first of all, I should say what I mean by a smooth map. So this is, as I explained here, this is a homeomorphism between open subsets in Rn. And we say that it's smooth if, what does it mean that a function on an open subset to Rn is smooth? It means that every coordinate of this function has all partial derivatives of all order. That's what I mean by smooth. When I say smooth, I mean that it has all derivatives of all orders. C infinity belongs to its C infinity map. So in fact, so this condition implies posteriori that it's not only these maps are not only smooth, but they actually diffeomorphisms, because if you reverse the order, if you consider pair ji, the transition map is going to be the inverse to this. So not only this map is smooth, but the inverse to this map is also smooth. So that means that there are differomorphisms. So okay, so now we have a notion of a smooth atlas, and let's say that two smooth atlases are equivalent. Say A and B. Equivalent if the union, right? An atlas is a collection of charts. So I can take charts of A, I can add to it charts of B. So this is definitely an atlas. And my requirement is that it's also smooth. Okay, so what does it mean? So you have one open cover by charts of A. You have another open cover of the same manifold M. So, and this way you get more transition maps from open charts of A to open charts of B. And my requirement is that these new transition maps are also smooth, right? So, Very good. So a smooth structure and that's kind of the main concept, at least of today's lecture on M, is an equivalence class. Of smooth surfaces. Okay. So what is really the meaning of this definition? So in this course we are going to do calculus on manifolds. So in particular, we are going to talk about smooth functions on manifold. And well, so if you have a topological manifold, well, locally it's homeomorphic to an open subset of Rn. So of course we all know what a smooth function on Rn is. But so if you choose a different homeomorphism, then well, of course the space of smooth functions is not preserved under composition with an arbitrary homeomorphism. So it wouldn't allow me to define smooth functions on M without an extra structure. So this kind of equivalence class of smooth atlases is, as we're going to see in a second, precisely what one needs to define notion of smooth function on M. So let's see how it works. So we would say that suppose I have smooth structure M and an equivalence class of smooth atlases. Smooth structure. Then, well, manifold together with its smooth structure is called a smooth manifold. So suppose I have a smooth manifold, and suppose I have an open subset, arbitrary open subset of M. So, and suppose this is open, and suppose I have a function on V to M to R. We say that F is smooth if the following is true. So so my A is again this collection UI VI. If so UI is identified with some by these maps with some WI in Rn. This is my VI. If the following is true, so let's take if for any I, if I take my function and restrict it on the intersection, if I take Fi of V intersected with UI, and I apply first phi inverse, and then F, that gives me a function on an open subset. So here I have V intersected with UI, that's an open subset, and it lands here. So this is phi I of V intersected with UI. So, and here I have my function f, which is a function R. So I look at this composition here, which is, this is phi I, so I take phi I inverse. And it lands in R. And so my condition, again, so this is the beginning of the definition. So a function on V is said to be smooth if all these functions defined on open subsets of Rn are smooth. Okay. So, and again, smooth here means that it has all partial derivatives. So, clearly, this property of a function being smooth depends only on the equivalence class of an atlas. Because if I compose a smooth function on an open subset of Rn with a diffeomorphism from one open subset of Rn to another, the composition is still going to be smooth. Composition of smooth functions is smooth. So, so for every, and it's also clear that every smooth function is continuous. So a smooth structure on my manifold M defines a subring, if you wish, of in the ring of all continuous functions. This is a notation that I'm going to use for continuous functions. And this is smooth functions. Okay, so in fact, this is kind of the most important attribute of a smooth structure, which determines smooth structure uniquely. If you know which continuous functions on M are smooth, then you know the smooth structure. The precise meaning, let me give you formulate this as a important exercise. So suppose I have two smooth structures. So assume that smooth functions on M with respect to one atlas, with respect to one smooth structure, is the same as smooth functions with respect to the second smooth structure. So this equality really makes sense because these are subrings of the rings of all functions or continuous functions. So I'm asking these two subspaces be, well, these two spaces be equal as subspaces of this large group. Then the two smooth structures are actually equal, so that the two smooth atlases are equivalent. So a smooth structure is determined by global smooth functions. So I'm going to use this exercise many times. So well, in order to define a smooth structure on a manifold, on a topological space, well, there are two ways of doing this. You can either construct a netlist, construct a collection of charts that cover M with smooth transition maps, or you can first define the ring of subring of the ring of continuous functions, which are called smooth, and then show that, well, then you know that this subring comes from a unique, not more, well, there exists at most one smooth structure that gives you this subring. And then maybe by some, well, you need usually some additional argument to show that that such a smooth structure exists, but at least it determines it's unique, right? This subring. So, so this is an easy exercise. So maybe I will just give you two, well, kind of a hint. This is very important. So hint is the following. So hints. Well, first, you prove a local statement. So if you have U and W in Rn, open subsets, and a map from U to W, then phi is smooth if and only if for any function f in C infinity function, for any smooth function on W, the composition, so you take f and then phi, is a C infinity function on U, right? What you need here is the, well, in one direction it's obvious, it's just the fact that the composition of smooth functions, smooth maps is smooth. In the other direction, well, it's also, it's not difficult at all. So this is one ingredient. And the second ingredient is that you need is the following. So, so here we make some global assumption, right? That the global smooth functions defined on the entire M are the same. And in order to apply this, you need to know that there are sufficiently many smooth functions defined on all M. You need to know how to construct it, right? And so what you use here is well, kind of a special case of what's called partition of unity. So if you so this is kind of one hint, and another hint that you need here is the following statement. Suppose you have a smooth function on so U is in Rn, and f is a smooth function on U. Oh, this is open. Then there exists for every point in U, there exists a smooth function on Rn such that f is identically equal to f tilde on some neighborhood. of B. So you have a map, smooth map from an open subset U to R, and you have a point. It's not necessarily it's not always possible to extend this smooth map to a map from R2 to R, right? Because your function can, say, approach infinity when you approach the boundary of this disk. But you can first take a smaller, maybe disk containing point P, restrict your function f to this smaller disk, and then this restriction you can extend to a function on R. Okay, that's the statement. That's kind of the second hint you need here. And so the construction is not difficult. It uses the existence of a smooth function, say, on R, which is equal identically to 1 on interval from 0 to 1, and which is equal to 0 outside of interval, say, from -1 to 2. Okay. Very good. So so we defined a notion of a smooth structure, and for a manifold with this, for a smooth manifold, we defined smooth functions. They actually form what's called a sheaf, in the sense that restriction. So for every V, we have smooth functions on V, and if you restriction of a smooth function to a smaller open subset is also smooth. It's obvious. Very good. And so the last, well, I think almost the last definition I want to make today is, so I'm ready now to define what a smooth map. So suppose I have two smooth manifolds. And a map. Oh, sorry, maybe I want to call psi. So let's say that psi is smooth. So a map between smooth manifolds is called smooth if the following is true for any smooth function on it. Its composition with psi is smooth. So f composed with psi is a smooth function. So now we say that psi is a diffeomorphism if psi inverse, well, first of all, it exists, and secondly, it's also smooth. So the exercise above shows that the identity map from M with one smooth structure to the same manifold M with another smooth structure is a diffeomorphism if and only if the two structures, smooth structures, are actually equal to A. So that means that A is equivalent to B. That's precisely the content of this statement. So that smooth functions as a subring of the ring of all functions determine the smooth structure. Very good. So now, so let me give you some examples. Oh, maybe before I go to examples. So here is another comment I should make. So suppose so this is kind of a natural definition, at least if you believe to the exercise that I explained above. But it's equivalent to you can so here is another maybe exercise that's important. So suppose that that I have a smooth map. Smooth. Then it's true that that pullback of a composition of psi with a local smooth function is also smooth. So let me explain this. So then for every u in n open and f, which is C infinity function on u, function psi composed with f is a smooth function on psi inverse of u. Okay. So more generally, it's true that a restriction of a smooth map of smooth manifolds to an open subset is also smooth. So if I have a manifold with a smooth structure, its open subset, any open subset of M, also acquires a canonical smooth structure induced by A. And a reasonable definition of a smooth map definitely would be such that open embedding is smooth and the composition of smooth maps is smooth. So this is something that we must have, and if we do not have it, it would mean that the definition should be modified. But in fact, it's a corollary of that global state. Okay. So now I want to give you some examples. Examples of smooth structures. Okay, perhaps let's start with something. Let's start with a sphere, Sn. So Sn is a collection of vectors. Sorry. Sorry. Okay. Sorry about this. I forgot to turn on Skype. Okay. So so I take vectors in Rn plus 1 such that sum of coordinates xi squared is I0 n is equal to 1. So that's clearly a topological manifold. Let's define a smooth structure. So I define a smooth structure by constructing explicitly a smooth atlas. So for every I from 0 to n, define u I plus to be a set of vectors in a sense with xi say greater than 0. And similarly, ui minus is a set of vectors where xi is less than 0. So this is open upper hemisphere. Well, not upper, it depends on what I is, yes, right? So this is half of the sphere. This is open half a sphere. You take well the part which belongs to open upper half space, and this is lower half space. So then for every I, we have a natural homeomorphism between ui and just the disk in open disk in Rn, where D is well set of vectors y in Rn with absolute value of y less than 1. And the map takes x0, xn and sends it to y equal to x1, sorry, x0, xn, and xi is skipped here. And so you just discard one of the coordinates. So geometrically, you take this upper hemisphere and project it to the xy plane. Or, so it depends on I, so you project it to also to yz plane and so on. So clearly, this is a homeomorphism. And so claim, an easy claim, an exercise, is that this collection ui plus phi I plus minus is a smooth atlas. Okay, so it defines a smooth structure on a sphere. Now, this is one way to construct smooth structures. So let me give you another example. So let's important example, Grassmann variety. Grassmann manifold. So so we fix some integers n and m, so as a set, the Grassmann manifold consists of m-dimensional subspaces linear subspaces W inside R. Well, dimension of W is equal to M. For example, if M is equal to 1, this is the set of all lines in Rn. So it's also called the projective space. So I defined this as a set, and I will not give you, well, I will define a topology and the smooth structure on this set the same time by providing an atlas, which a smooth atlas on. Well, I will give you a collection of subsets of the Grassmannian, such that and collection of charts with smooth transition maps, and I define topology on the Grassmannian using these charts. So, well, so let's construct charts. So for every linear subspace, say W prime, in Rn, of the complementary dimension with dimension of W prime equal to n minus m, we can look at subspaces. So let's consider the collection of all subspaces, and this I will call this collection U prime. So this consists of all points of the Grassmannian, n m, right? So with the property that the intersection of W and W prime is 0. So we are looking at the space of all n-dimensional subspaces of a given vector space. We fix a subspace of complementary dimension, and we look at those subspaces which do not intersect W prime. So now let's construct a bijection between U W prime and well, canonically, this will be the space of all maps home over R, linear maps from W, from W prime orthogonal to W prime. Okay. So I will just explain how this bijection works. So, okay, so you have this W prime. This is W prime. And you have the orthogonal complement. The entire space is this Rn is equal to the sum of W prime and W prime orthogonal. So now let's consider an arbitrary subspace W, a point on the Grassmannian, with this property. So here is a picture. So this is my W. And what I know is that this W does not intersect W prime. It means that this projection, the orthogonal projection, is an isomorphism. Is an isomorphism of vector spaces. Or equivalently, it means that this W can be thought as a graph of a linear map from this vector space to this vector space, right? So W is the graph space here. W is graph of a linear map. So, and of course, the space of all linear maps is identified with R, with matrices. So this is R M n minus m. So, so we define a topology on Grassmannian by declaring this set to be open. This is the weakest topology, such that these sets are open, and this map is homeomorphous, right? So this makes the Grassmannian into a topological manifold. We also computed its dimension is equal to m times n minus m. But in fact, I claim that this is a smooth atlas. So exercise, if you consider the entire collection, U W prime and this phi W prime is a smooth atlas. Okay, very good. So this is this makes Grassmannian into a smooth map. So here is another example. So let's take for M just R. Well, R is there is a natural smooth atlas on R that consists of I can take just smooth atlas consisting of one chart, identity map, and this defines a smooth structure on R, tautological one. But I can also define another smooth structure on R. I can take for open chart, well, also an atlas will consist of one chart, but the map is going to be x goes to x cubed. Okay. So this is also a homeomorphism, and it defines a smooth structure on R, which is not equivalent to this one. That is just because the function cube root of x is not smooth. So this observation of course, you can use it to construct infinitely many smooth structures on R, right? So not equivalent smooth structure. Well, though this structure is obviously not equivalent to the standard one, R equipped with the first smooth structure is diffeomorphic to R equipped with the second smooth structure. And the diffeomorphism is given by the map that takes x to x cubed, tautological. So this does not, in a sense, give me a new smooth manifold. So, in fact, you can ask whether, given a, say, a topological manifold, whether it's possible to have two smooth structures which give non-diffeomorphic smooth manifolds, right? For example, I can look at the standard sphere and look at all and try to construct, ask whether there exists again a smooth structure in a sphere such that, which is not diffeomorphic to the standard one. This is not an example of such a situation. This is a really kind of a delicate question, and it was a breakthrough in differential topology when John Milner found that S7 seven-dimensional sphere has 15, precisely 15 smooth structures. So by again, so there are precisely 15 smooth manifolds which are homeomorphic to S7, but which are not pairwise diffeomorphic. Okay, so now I want to well, I want to conclude very soon today's lecture. Maybe I'll just give you one more example, well, a very important example. So there is another way to construct smooth structures, which I alluded to earlier. So let's consider the following. Let's take a smooth function on Rn. And let's define them to be the level set. So set of points in Rn given by equation f of x equal to 0. Right? So this is a closed subset in Rn, so it's a in particular it's a topological space. So I'm going to construct a smooth structure on this end. So, well, in fact, in general, this is not even a topological manifold. So, so let's assume the following. That for every point in P, in M, the differential of my function at point P is not equal to 0. So, well, that by definition, if you So differential is something that, well, currently you know what differential function on Rn is, but well, that simply means that dfi, df over partial derivative at point P is not equal to 0 for some I, right? Then there exists a unique smooth structure on M with the following property. So instead of defining charts, I will just tell you what smooth functions on M are. And as we already discussed, a smooth structure is determined by this. Okay, so there is a very natural choice. So we look at all, say, continuous functions on M such that there exists a function on Rn whose restriction to M is this. So smooth functions on M are precisely restrictions of smooth functions on R. So it requires a proof that a smooth structure with this property really exists, but the uniqueness is clear because C infinity of M determines the smooth structure. So let me comment how you construct a, well, this is kind of one way to describe a smooth structure, which is very convenient because it's very short. So you can also construct coordinate charts, and actually, in order to prove the existence, right, the existence part here, you need to do it. And I will explain how you do this.
Excuse me, last question.
Yes.
Earlier we had this example with two maps of R on itself. Yes, X and X2.
Yes.
My question is, are they in the end equivalent or not? So we consider them not equivalent. Is it?
Okay. So let's go back. Such atlases, these two atlases, define smooth. Well, this methodologically, these are smooth are two non-equivalent smooth atlases on R, right? Why they're not equivalent? Because what would it mean that these two atlases are equivalent? It would mean that if you look at the following diagram here, this transition map, and this transition map is well, the map I'm actually interested in is this one, which is cube root of X, right? This transition map is not smooth. Therefore, if I consider R with an atlas consisting of these two charts, it's not smooth.
Okay, and it
Meaning
means that
the two atlases are not equivalent.
okay, so and it gives us
in particular the smooth functions with respect to one smooth structure and with respect to other smooth structures are different. So well, if you look at the first smooth structure, then, well, it's a standard one. So function f is smooth if it's simply has all derivatives, usual sense. So this is smooth if if you look at the ring of smooth functions for this smooth structure, it's the following. It consists of all continuous functions such that f of x cube has all derivatives, right? For
Yes, okay, that was
example,
my question.
function cube root, yeah, with respect to x. For example, function cube root of x does not have even the first derivative at 0. But if you substitute here for x cube, it's definitely becomes x, so it's smooth with respect to the stuff. Well, it has all derivatives. So as you see, this is a very good question, and you can see that these two structures are different, non-equivalent, by observing that the ring of smooth functions are not equal as subring of the ring of all functions.
And it means that in the example with the sphere, we have 15 different classes of.
No,
different.
this is much more interesting. Although, these are this gives you two different smooth structures on R. These two smooth, the two smooth manifolds are actually diffeomorphic. So okay, maybe so here is a comment. So suppose you have M and with a smooth lattice A, and M with another smooth lattice. So it's clear that A is equivalent to B if and only if the identity map from M to itself is a diffeomorphism. So in this example, the identity map from R to R, where the first copy of R is equipped with the first smooth structure and the second copy of R equipped with this smooth structure, is not a diffeomorphism. However, you can construct a different map, right? It might happen that you can construct a map from M to M, which is a diffeomorphism. And in this case, the map would be just this one. It takes x to x. When I say that S7 has 15 smooth structures, well, I meant not pairwise diffeomorphic. It means that I have really 15 smooth manifolds, each of which is homeomorphic to S7, but which are pairwise not diffeomorphic. Not only that, well, I do not even identify them, so it doesn't really make sense to say that the identity map, but well, they are not pairwise diffeomorphic. So it's much stronger. So of course you can construct easily, generalizing this example or modifying this example. You can take S1, for example, and you can construct a smooth structure on S1, which is not the standard one. Yes? This way, the identity map would not be diffeomorphism. But still, it's not possible. Any smooth manifold which is homeomorphic to S1 is actually diffeomorphic to the standard S1. So it's not possible in dimension 1 or 2, and even 3.
Okay.
So this is a delicate. I will explain a construction, at least, of this smooth structures. We'll see if we have enough tools to give a proof. So very good. Let me explain a proof of the existence. And again, I will prove the existence by constructing a smooth atlas. And the construction is based on implicit function theory. So by implicit function theory, for every point in M, there exists an open neighborhood such that U in Rn is the graph of a function. So say xi is equal to g x1 xi xn. Right? This equation locally, this equation that f is equal to 0, can be locally solved. You can find this smooth function with this property. So that means that M locally looks like a graph. And then, so you can consider projection. So from this U to an open subset in Rn minus 1, sending x1 xn to x1 xi xn. And this projection defines a homeomorphism from U to an open subset in Rn minus 1. And that's how I define an open. Well, this is a chart, and I claim that so you can do it for any point P. So the collection of all these charts form a smooth atlas. That's the claim. So it forms a smooth atlas, and it's clear that if you use this chart to define smooth functions, so smooth functions are precisely the functions that correspond to smooth functions on Rn minus 1. So these are, I look at functions on this graph, which are smooth as functions in all these n minus 1 variables. And those functions are precisely the functions on the graph, which are restrictions of smooth functions on Rn. So this proves two things. That first of all, well, I gave you another construction. I construct a smooth structure in M by presenting for you a smooth atlas. But it also shows that the smooth atlas has a property that smooth functions corresponding to the smooth atlas as precisely this. And this is one-line definition. So, for example, you can use it to give another description of a smooth structure of an ascent. So Sn is given just by one equation, and it has the property that the differential of this function, sum of squares minus 1, does not vanish at any points on the sphere. So it comes with a canonical smooth structure. Okay, so this is a very useful general construction. It has a generalization, straightforward generalization. So this is probably the last thing that I'll say today. Generalization. Suppose you have collection of m functions. So you take vectors in Rn with the property that f1 of x equal to fm of x equal to 0. So this fi are smooth. And the condition, so here the condition was that the differential does not vanish. This was the condition, and so in this setting, the condition will be that rank for any point P in M, the rank of the Jacobian matrix, which is T Fi J at point P, is maximal possible, which means that it's M. Then, sorry, this is, that's not what I meant to say. This is, so then there exists a unique smooth structure on M with global smooth functions equal to those functions, continuous functions, such that there exists f tilde Rn this restriction to M is M. Okay, and the proof is similar to this. So it's you can think of this as locally. This M can be thought as a graph of a map from n minus m dimensional open subset of Rn minus m to Rn. And this is by general implicit function theory. So it's locally looks like a graph. And then you can use projection to define. Okay, so I would like to stop here. So once again, please, I want to ask you a favor. Please send me a message, and so yeah, that's important. So use email address.
You mean message here in Zoom or in
No,
email?
no, using Gmail. This address. Gmail. Okay. Yeah. So if you are going to participate in this and this course. In particular, if you want to register, so then you need to do some homework. So please send me a message. And even if you are not going to register, but going to participate and you are interested, please send me also send me a message. So I will reply to your message with a link to the video and notes and also homework. Any questions on today's lecture?
Yes, I have a question. Is it true that mentioned exotic structures on S7 could be realized as hypersurface in R8? Or some estimation, or it's just an abstract statement?
No. Well, first of all, it can be shown that any smooth manifold can be embedded.
Yes, of course. But ordinary sphere could be embedded in R8. Yes.
I'm not sure. I don't know whether it can be realized as a hypersurface.
Well, okay. And
So
construction.
What is the smallest embedding dimension? What is the embedding? Yeah, that's good.
You mean 15? Yes.
Yes.
Okay. And do you planning to discuss such topic in your course?
I cannot. I will not prove that there are precisely 15 exotic smooth structures. This is far beyond the scope of the course. But hopefully, I will be able to construct one example of exotic structure and show that it's not diffeomorphic to.
That's already great. Okay.
Excuse me.
Thank you.
So, do you understand it correctly that all these 15 things, they are all basically the same sphere, but we just put the maps in some other way.
No.
But it's just basically the same I don't know, figure, but we just write down coordinates in some other way, like in x cubed instead of x.
This is a sort of a mathematical way of expressing what you are saying is that all these spheres are homeomorphic to S7. Or are you asking something else?
Yes, they're all homeomorphic to S7. So, but the difference is that, like in this example with R, we have x and we have x cubed, and maybe in this S7, maybe is it something like this? Like just
no, it's again. So as I explained, it's this example with R is really stupid because this exotic R is actually diffeomorphic by a non-identity map to the standard R. This does not happen with exotic spheres. But yes, you're right that in principle you can construct these exotic structures by just taking the standard sphere and defining in coordinates explicitly a smooth atlas in a different way. That's possible.
So,
but I don't think that you can feasibly say, for example, show that you definitely, so this seems to be like completely out of reach problem to show that there are precisely 15 non-diffeomorphic seven-dimensional spheres.
I want to mention that there is a note in Hartshorne's algebraic geometry which mentions that these exotic spheres can be realized in C5 by explicit equations, and it follows easily from this note that it can be embedded in R9, I think. So the embedding dimension is pretty low. It's not.
I see. Where is this node?
At the very end, in the chapter of surfaces, it mentions that a singularity.
What about the section?
Well, it's in the very end. I don't remember exactly.
I see. So at the end of the chapter on surfaces.
Yes, it mentions that there is a specific singularity of an algebraic surface in C5, such that if we intersect it with a small sphere, with a small S9, then the resulting intersection will be homeomorphic to S7 with an exotic smooth structure. So it lies in S9, and hence it can be embedded in R9.
Okay, so maybe very good. Yes. So thank you for drawing attention to this. Any more questions?
Yes. Where can I read something about what happened in this lecture?
So that's a very good question, and the answer is for the first part of this course, I'm going to use a book by Lee, and the title of the book is Introduction to Smooth Manifolds. Well, this is really very slow. Although it's graduate text in mathematics, smooth manifolds. Perhaps if you send me a message, and if you are interested in, I can send to you a copy of this book. It's it's very kind of, it has too many details, so it's very slow. For example, I think today I covered about maybe 30 or 40 pages from first 40 pages from this book. Though it's very thick, maybe 300 pages, I think we will do it very quickly. It doesn't have that much content, so
what about the exercises? Where can I find some exercises like?
Where you say again?
Where can I find some exercises?
Well, first of all, I will send to you a page with a link to some exercises that we will discuss. But also this book, the advantage of this book is that it has plenty of exercises. They are mostly kind of just on understanding definitions, but still it's very, very important.
Okay, thank you.
I was wondering also, so let's see. So how many of you are actually here on the physically on the department? So well, we see. Okay. So I see some probably. Yeah. So until we will continue in Zoom until all people who are willing to come can physically do this, right? So far the border is effectively closed for most countries, from citizens of most countries. So until the time it's open, so we will continue. Okay. So okay, let's adjourn here. So see you in a week, the same time. And meanwhile, I will send you some problems for the problem session. Thank you very much.
Thank you. Bye.
Bye.